In the following talk, Lee Overman and I would like to present an archaeological perspective on human spatial thinking. I will use the first half of the talk to discuss early developments in hominin spatial cognition from about 3.3 million years ago to about 500,000 years ago. What I hope to show is that some important developments in human spatial cognition occurred long before we were officially human. I will then pass it on to Dr. Overman, who will discuss some more recent developments. I'd like to start off with a fairly well-known example from the recent past, which is Ernest Shackleton's journey from Elephant Island in Antarctica to South Georgia Island, which was a journey of about 1,500 kilometers across the stormiest oceans on Earth. This was a remarkable bit of sailing. It was also a remarkable bit of navigation. Of course, he had some help. His navigator was a fellow named Frank Worsley, and Worsley had a sextant and an accurate chronometer. And using these assists, he was able to navigate a perfect journey across the ocean. But this was actually not really unique. Micronesian navigators do similar things. For example, they were able to sail their outrigger canoes from Saipan in northern Micronesia all the way to central Micronesia down to Puluwat down here, which is a journey of about 600 miles or about 900 kilometers. And again, it's across the open ocean. And in this case, they don't have a sextant and they don't have an accurate chronometer, but they do use a system of knowledge that is based on a very clever version of dead reckoning, which I think Dr. Overman will be talking about, and also celestial navigation using star positions. But what I wanted to talk about today a little bit is how did this evolve? That is, where did this ability come from? And how old is it? You know, how long have we been able to do this? We humans use two basic methods of wayfinding and a number of sort of hybrid intermediate forms. One form is known as route following, and you get this a lot from Google Maps. And if you ask how to get from point A to point B, this is usually what you get. And for example, on the right, you see after Park Street, you need to take a right on Summer Street and to Holland Street and so forth. And then, so basically it's moving from a system of landmarks, from one landmark to another landmark. And it's a very effective way for moving about landscapes one is already familiar with. It doesn't work very well for landscapes you know nothing about. So the second system we use is often called survey knowledge. And this is where you use some kind of external spatial framework to orient yourself in space and to determine the location of your target and how to get from your current position to your intended position. This is what we use in usual maps that people are familiar with. And that perspective takes a bird's eye view. That is as if you're looking down on the surface of the Earth. There are other ways of doing it, but that's the most familiar one for us. Turns out that these two systems of wayfinding, which is the preferred word, rely on different cognitive systems. Route following, for example, relies on very basic topological relationships. Turn left, turn right. It's inside, it's outside. And it also relies a lot on long-term memory. That is, one's ability to remember landmarks on the landscape and remember what choice to make at a particular landscape. And humans have developed a lot of very interesting mnemonic devices for doing this. One that a former student of mine talks about a lot was used by the Comanche in the southern plains of the United States when they were raiding into Mexico. And they would sit down around a fire and ask the intended participants to memorize a series of landscape features. And after they had succeeded in memorizing them, they were recorded as little marks on a stick, so with that, when they were actually moving across the landscape, they could move down one notch to the next, remember what the landscape feature was supposed to be and what they were supposed to do when they got there. And this is, again, a form of route following. Survey knowledge relies on some other cognitive systems, in particular something known as allocentric perception, which is one's ability to construct a third perspective or a second perspective that you don't have direct access to. That is something that you cannot see. You have to imagine that perspective. And it also relies on some understanding of spatial quantity, that is spatial amount, that is how far one has traveled. Now, my particular specialty is cognitive archaeology. And what can a cognitive archaeologist do to add to a study of human spatial thinking? Cognitive archaeology, by the way, is a fairly simple idea that you look at archaeological remains and try to reconstruct something about how people were thinking in the past. There are two pieces of information that cognitive archaeology supplies to the study of cognitive evolution. One is the timing of developments. That is, when did something occur? And more importantly, in what sequence did these things occur? So for example, in our case, we could ask the question, did route following and survey knowledge evolve at the same time or not? Did one precede the other? And as we'll see, it's almost certain that route following has been around longer than survey knowledge. Second thing that archaeologists can supply is the context. That is, what was the world like, in a sense, when these particular abilities evolved? Which hominin ancestor first demonstrated the ability? How did its way of life select for that particular ability? Now, there are a lot of caveats that go along with cognitive archaeology. We have to keep in mind that the archaeological record is actually a relatively poor sample of what people were doing in the past. There's also a sliding scale of resolution. That is, the deeper we look in the past, the less preserved and the less we know. For example, until very late in the Stone Age, there's almost no direct evidence of wayfinding per se. I think Lee will talk about one example for Neanderthals. When we get up closer to the modern world after about 200,000 years ago, we can begin to see some things about wayfinding, but prior to that we can't. So what do we have to do? We have to be clever. We have to try to extract useful insights from the evidence we have in abundance, and that is stone tools. And the earliest stone tools are about 3.3 million years old. Now, for the benefit of people who are listening who don't know anything about stone tools, what I'm going to do is play a video. It's about 7 minutes long, prepared by Nick Toth from the University of Indiana. It presents basic stone knapping, that is how you make a stone tool, and it also introduces an important tool type known as the hand axe, and I will have a lot to say about hand axes. So with any luck, this will work.
My name is Nicholas Toth. I am the co-director of the Stone Age Institute and a professor of anthropology at Indiana University. And I want to show you what our ancestors started doing about 2.5 million years ago that we can see on the African continents. The earliest archaeological record are very simple stone tools, and they discovered around this time that if you took two natural cobbles, say from a gravel bar of a river, you could hit one against the other one and knock off these razor sharp pieces of stone that archaeologists call flakes. So in a matter of a few seconds, I'm producing these very sharp razor blade-like materials that can be used for, say, cutting up the carcass of an animal that you might kill, or maybe you find that's been left by carnivores and a little bit of meat left on the bones that you can cut off. So these are literally razor sharp. If I were to drag this across my finger, I would cut myself quite badly. So when you think of early stone tools, don't think that they're not razor sharp. They're as sharp as a surgical scalpel. And we can use these for a range of activities, as our ancestors did in the early Stone Age, butchering animals, working wood. Say you want to make a spear for hunting, or a digging stick for digging up roots and tubers from the branch of a tree. These are great tools for the shaping that you would do for that. And so we see this trajectory in human evolution starting around 2.5 million years ago of these very simple types of stone tools. And it's soon after that, by about 2 million years ago, that we have really good evidence for the expansion of the human brain, for the spread out of Africa shortly after that, the reduction in the size of the teeth and the jaws of our ancestors as well. And starting about 1.5 million years ago, they started getting more ambitious and making forms that we call so-called hand axes. They were probably held in the hand and used as cutting tools. This would be one, it's a more refined one from perhaps about 0.5 million years ago or so, made out of flint. And so the idea of this is you would take a larger piece of stone and kind of imagine that form in the middle of it. And then again, using a hammer, slowly but surely marching around the edges and knocking off flakes. So I'm using the scar of the flake that was just knocked off as a striking platform to go in the other direction. And the idea is you want to march all the way around this piece. So I'm not thinking too much about the final shape yet. I'm just kind of trying to produce an edge around the circumference of this piece. Okay, and so it would take me about another 5 minutes to go all the way around this. And then the next stage that our ancestors learned to do, that's called hard hammer percussion, where you use a hard hammer to knock off flakes. And another thing they learned to do, which is really interesting and somewhat counterintuitive, is you totally steepen the edge. You dull the edge by removing these little flakes with a smaller hammer, and then grinding the edge. And then you take a softer material. It could be a piece of hard wood, a fragment of elephant tusk. In this case, I'm using an antler of a deer. And you're biting right into the edge. And you're able to remove much longer, thinner flakes when you do that. And this is a way of controlling flaking. Do it one more time. You get a much thinner product at the end of it. And this is called soft hammer technique. I'm going to try to drive a flake off of this side by striking on this side. You can see how I did that. And by doing that, going around, you can carefully shape the edge, thin it, and make a superb butchery tool. And when people ask, why did they bother to make something this big? They were butchering large animals, sizes of zebra and buffalo on occasion. These are big mammals that weigh hundreds and hundreds of pounds. And would you rather use a razor blade for butchering one of these animals, or would you rather use basically a two-fisted tool like this? You have a lot more cutting edge, a lot more weight behind what you're doing as well. And so when we look at the history of technology, you're seeing changes in the refinement of stone tools over time. By the time you get to Neanderthals and early modern humans, they're probably starting to heft tools onto handles, either using some kind of adhesive material like pitch from a pine tree, or by using sinew or other material to lash tools together as well. And so we see this progression and refinement of technology through time, especially with stone. But starting around 80,000 years ago, we're also seeing refinement in bone working, that they're starting to make bone tools for the first time as well. And we strongly feel that technology is a very important element in the evolution of the human brain, that without technology, we wouldn't have the high quality diet that we need that's driving that brain evolution. Your brain is about 3% of your body weight, but about 20% of your energy intake. So it's a very expensive organ to have. So we must have had a very good reason to have a large brain. Probably has to do with becoming very social animals. We're living in larger groups. We have to deal with a number of individuals politically and socially. And so more intelligent animals are able to interact socially in a better way. And so probably another payoff of these larger brains over time is that we become more inventive and experimental and try new techniques of making and using tools as well. And we become the consummate, the most important dedicated tool maker in the history of the earth as we are today.
All right, why isn't this working? Okay, let's do this. Okay, there we go. Okay, you just heard Nick Toth talk about basic stone napping. This is a picture of Nick Toth's brain under a positron emission tomography scan. This was done about 20 years ago. And I present this to give you some idea of what's going on in the brain when Nick Toth is stone napping. And in this case, what Nick did was just knock off basic flakes for about 5 minutes after they'd injected him with a radioactive tracer. Then he jumped in the machine. They gave a scan of his brain. There's a couple of things I want to point out. First of all, up here, if you can see this, okay. This is the superior parietal lobe, and it's involved in spatial cognition. You can see it here also. And what this scan really tells you is that stone napping is a visually guided motor procedure, and that guiding action in space is one of the important things that goes on in stone napping. Interestingly, what you don't see here is much activation of the frontal lobes. Turns out Nick Toth is an expert stone napper, and as a consequence, he doesn't really, when he naps like you saw, doesn't really engage the major working memory processes of the brain because it's more or less an automatic procedure for him. So if we're going to talk about the evolution of spatial abilities, a natural place to start is to talk about non-human primates. What do non-human primates do in terms of wayfinding? What is their spatial cognition like? We could go into a lot of detail about this, but I'm going to sprint through it. If we look at chimpanzees in their natural circumstances out in the wild, if they're traveling from point A to point B, they almost invariably take an established path. They almost never go across country and almost never break a new path. That is, they follow established routes. So this would be a kind of route following. And this is how primates get around their territories. And especially anthropoid primates have a detailed memory of the resources that are available in their territories and where those resources are located, and they can get to them efficiently using route following as a technique. We can also ask about this sort of general spatial cognition. This is a little harder to do. About 60 years ago, there was a flurry of interest in what was called chimpanzee art. And a lot of zoos made a lot of money off of selling chimpanzee art. And where they would do this, they'd get a compliant chimpanzee. That's a bit of an issue in and of itself. They'd sit it down in front of finger paints and basically ask them to create. And this example on the right is an example of a chimpanzee painting. that was then sold for thousands of dollars. What they don't tell you about this is that whoever is assisting the chimpanzee has to take the piece of art away, because the chimpanzee will continue to do this until the whole sheet is covered in brown. Because they enjoy the process, they enjoy the color. They're not actually making images. They're engaging in a motor procedure, very interesting and profitable for zoos, but it doesn't really turn out to tell us very much about spatial cognition. What most non-human primates use in their basic spatial repertoire are what we would call topological relationships: left and right, up and down, inside, outside, those sort of basic spatial relationships. And this happens to be true of the earliest stone tools. So you saw Nick Toth making one of these earlier, from about 3.3 million years ago. And I should say that Nick Toth's video was made before a new site was found in 2015 with stone tools that date back to 3.3 million years. But between 3.3 million years ago and 1.8 million years ago, that's a fairly long time, hominine technology was pretty simple. It consisted of knocking flakes off of cores, using the flakes for cutting, using the cores for crushing. Not much happens. The basic the basic spatial repertoire of these early hominids were basic topological relationships. They were not interested in the shape. Technology was pretty simple. They were not interested in the overall shape of the tool. They were not really very interested in the shape of the edge. They were interested if it was sharp or if it wasn't sharp. So this prevailed for 1.5 million years, which is really quite a long period of time. But about 1.8 million years ago, this artifact appears on the scene. It's called a hand axe, probably slightly a misnomer. It probably was never used as an axe, or very rarely ever used as an axe, but it was probably held in the hand. And the way to understand a hand axe is that it was the hominin solution to the problem of producing a large handheld cutting tool. And John Gallett, who is arguably the world's authority on hand axes, has come up with what he calls a sort of ergonomic design explanation for hand axes, that hand axes instantiate these 6 ergonomic design features. One is called a glob butt, which is basically down here, which is basically the end you hold in the palm of your hand. So it's a little thicker, it's a little heavier, it allows you to get a good grip. Forward extension, which is the extension away from the palm. Remember, we're trying to produce a effective cutting tool and with a long cutting edge. And so if you extend it away from the palm, you get a more effective cutting tool. Edge support is making the bifacial edge. You saw Nick Toth doing that. Lateral extension is interesting. It's this dimension. It turns out that if you try to make a cutting tool like this that's too narrow, it twists in the hand. And to cut down on the twisting, you need to give it some lateral heft. And that's what this does. But then stone tools are heavy. And if you're using them, they're very tiring. So if you reduce the weight, that's helpful. And the only way really to do this with a large cutting tool is to reduce the thickness, because you don't want to reduce the length. You don't want to reduce the lateral extension. And then John argues for a bit of skewness for handedness. I don't actually agree with him about that, so we'll skip past that. How's that sound? So one of the features that appears very early on hand axes, and the one that actually helps us out a bit here, is something called overdetermination. So Gallett's ergonomic imperatives fall short of a complete account of hand axe form. The hand axe stone knappers often added features that were not essential to the artifact's ergonomic functionality. In other words, they overdetermined the form. And this overdetermination was linked, we think, to visual appeal, and it enables us to see some things about spatial cognition. Overdetermination in the direction of regular forms is the most obvious. Imposition of shape is one of the most salient features we see on hand axes. And the shape that they imposed most often was symmetry, almost from the very beginning. So this is a hand axe from Olduvai Gorge. It's about 1.69 million years old. The hominine stone knappers went to a great deal of trouble to produce a bilateral symmetry on a big flake of lava. And if you go back and look at the order of flake removals, which one can do if one looks at this very carefully, it's clear that the knapper flipped the tool back and forth, trimmed different parts of the edge in order to achieve this bilateral symmetry. So what does that tell us? First of all, we have to remind you a few things about visual processing. Visual information, travels through the eyeballs, passes to the occipital cortex of the brain, which does initial visual processing. Excuse me. Vision is arguably the best understood of the sense systems, and we share all of our visual system, almost all of our visual system, with non-human primates. So things like stereoscopic vision and color vision are things that we share with anthropoid monkeys and also with apes. So what happens with the imposition of form on artifacts? And this is the first interesting thing that we can see in the evolution of human spatial abilities. We saw earlier when we saw Nick Toth's brain that spatial cognition is primarily a temporal lobe function, a parietal lobe function. And this is something what is sometimes called the dorsal stream of visual processing. Shape recognition, on the other hand, that is the processing of shapes, occurs down here in the temporal lobes. And this is sometimes known as the ventral stream. So the first thing that has to happen for a hominid to impose a shape on an artifact is to coordinate these two systems, which are generally not connected to one another. And we assume it happens at some place in some kind of central control, if not working memory, some part of frontal lobe function. So if we go back to our FLK West hand axe from Olduvai Gorge, we see that the hominid who made this was coordinating the dorsal and ventral streams of visual processing in order to impose this symmetrical shape. Symmetry is an example of a good gestalt form, and recognition of symmetry occurs in cell groups of the fusiform gyrus of the temporal lobes. Now, it turns out that symmetry recognition is very old in an evolutionary sense. The ability to recognize a symmetry is shared with lots of organisms. And this is adaptive. Predators are symmetrical, food is symmetrical. It's a good idea to be able to see symmetrical things. But what's interesting here is the hominids start imposing this form on stone tools. They also imposed radial symmetry on stone tools. These artifacts are a little bit more recent in time. Ubediyah is about 1.5 million years old. This artifact on the left is very interesting. It's a very large artifact. It's 20 centimeters in diameter. Doesn't appear to have been used, and it's clearly modified. We don't know what they were doing with these things. It's kind of a puzzle, but they were clearly imposing a radial symmetry on stones. Louis Leakey suggested these were bola stones or they were used as projectiles, but you don't really need them to be perfectly round in order to be a projectile unless you're playing cricket or baseball or something. So for the next million years, after 1.5 million years ago, hominins very slowly acquired techniques that gave them greater control over artifact shape. Nick Toth talked about some of these in the video. They occasionally invested their hand axes with attractive aesthetic effects. And in doing so, they utilized some higher level visual processes, which I'm going to talk about next. But they also utilized regularities in shape that reveal some interesting things about abilities and congruency, which is a component of Euclidean thinking. So first, let me talk a little bit about what Helmut Leder calls implicit visual effects. These are effects that artists use today to enhance their visual presentations, and hominins use some of them as well. And then I'll say a word about allocentric perspective. The first of these implicit effects is known as peak shift. And if a stimulus provides pleasure, an exaggerated stimulus supplies more pleasure. That's basically what's behind it. It's an effect that's used a lot in political cartoons. So as you know, political cartoonists like to exaggerate the sizes and the shapes of structures as a way to make humor and also make political points. Like, you know, Donald Trump's orange hair is a great example, or Barack Obama's ears are another example of peak shift. But what we see in stone tools most often, the one that's most clear, is gigantism, which is making very, very large tools. This tool in the middle is a hand axe. It weighs well over 3 kilos. It probably was not used as a hand tool. It may not even have been used at all. And what the hominins did was invest a lot of effort to produce these very large stone tools. And there doesn't seem to have been much payback in terms of doing that. Even if you use the one in the middle two-handed, you would get tired very quickly. So we think they were doing it as a way to show off, as a way to sort of visually impress someone else. Gigantism is not the only form of peak shift. Another form is what I call hypertrophic forms, that is taking the basic shape of a hand axe and exaggerating it in some way. So the one on the left is a very long, narrow hand axe. The one on the right is what's called a twisted ovate, and I'll show you one of those a little bit later. If you turn this hand axe and look at it from the profile, it looks like the person who napped it held it in a hand and twisted it around the central pole. They have this nice S twist on the edges. They're very beautiful artifacts for the most part. A third form of peak shift is color. The hominins often selected clasts of raw material that had a beautiful color or beautiful quality to them. This one on the right is probably, I think, made in the running for the most beautiful hand axe ever found. If you look at it carefully, you can see it's made out of layered stone. It's actually a form of ironstone. And the napper made the basic hand axe shape and then scalloped the edges, went down the edges. So they made these little scalloped flakes along the edge that showed off the layered nature of the color. So this is an absolutely beautiful artifact. And again, it's a way to both invest the artifact with aesthetic appeal and perhaps advertise one's skill as a stone napper. I want to say a little bit about the second of these implicit effects, which is prototypicality. As I think many of you know, the way the brain assigns membership to categories is by resemblance to prototypes, not by trait lists, but by resemblance to prototypes. And the prototype of the hand axe is very close to a form called the hemilemniscate, which is, if you know about mathematics and the lemniscate of Bernoulli, a hand axe, this is a hand axe turned on its side, is very close to half of a lemniscate of Bernoulli. Now, I'm not arguing that the hominins understood mathematics in this sense, but there's a regular shape that's associated with hand axes, and it appears to be a regularization of those ergonomic shape forms that Gowlitz talked about earlier. That is, if you take that basic glob butt, forward extension, etc., and regularize it, this is what you get. And this prototypical form, you might call it a teardrop form if you don't want to call it a hemilemniscate, was the primary target for stone nappers for about 1.5 million years. And that's a staggeringly long period of time to have a single target for your technology. And we don't quite understand why that's the case. From an aesthetic point of view, the closer an artifact gets to this prototypical form, the more pleasing it is, the prettier we think it is, including us today. And so it wasn't just hominins 500,000 and 1 million years ago who were finding aesthetic appeal in these objects. This one I'm especially fond of in the middle, from the Israeli side of Gesher Bernat Yaakov. It's about somewhere between 600 and 800,000 years old. It's just a beautiful artifact in black lava. I want to say a little bit more about regular geometric forms, because Stanislas Dehaene, a French neuroscientist, recently made an interesting argument that people, that is modern humans, are sensitive to regular geometric shapes, not just symmetries, but all kinds of regular geometric shapes, pentagrams and so forth. We're very good at seeing these things. We can select them very quickly out of arrays of line drawings. Non-human primates don't seem to be. And he's done the research to support this, that we pick out regular geometric shapes very rapidly. Non-human primates don't. And Dehaene suggests that this perceptual bias is as important as language in grounding our abilities in mathematical thinking. I don't know about that. Some of you may have some thoughts about that. But what struck me is that regular hand axes, like we've been talking about, either reflect the initial stirrings of this bias towards regular shape, or, and I think this is a little bit more provocative, that stone knapping, making hand axes for 1 million years, may have been the avenue by which this bias evolved. No one's really examined that very carefully. I'm too old to do it. We'll let Lee take care of that, I think, is probably what we're going to do. The third implicit effect is familiarity. And this just simply means that something that's a familiar form to you will give you more pleasure than an exotic form. And we could argue about that a little bit. But this is really hard to detect in the archaeological record, because what you need are the products of a single social group. And we have almost no examples of that from the early Stone Age. The only example comes from the English site of Box Grove, which is a landscape that was exposed when sea level dropped for about 80 years. Then sea level rose again and covered the landscape. And we have hundreds of hand axes from this landscape, and they were probably all manufactured by the same social group. And you can see some examples on the right here. They look as if they were cut out of a cookie cutter. And in this case, it's very late. The hand axes are only about 500,000 years old, but the hominins were clearly following a community norm of some kind. Finally, this is sort of a roundabout way to allocentric perception. And if you recall, allocentric perception is the ability to construct a point of view not available to you directly, that either someone else has or that an imaginary perspective has. And 30 years ago, evolutionary psychologist named Erwin Silverman put together a number of experiments investigating allocentric perception. And what he discovered is that this is one of the important abilities in mental rotation. You know, those rotating box tests you get on psychometric tests. Allocentric perception correlates very strongly with one's ability to do mental rotation. And furthermore, he then examined whether it played an important role in human wayfinding. And the way he did this was he took students out in the woods, blindfolded them, asked them to point home. And it turned out that we're pretty good at that in some ways. That is, if you take a student, you walk them through the woods and then ask them to point where they came from. Some students are really good at it. Other students are not so good at it. Now, the point Silverman was trying to make was one about sex difference in spatial cognition. I'm not going to go there. That's a different topic. But what he was suggesting is that allocentric perception evolved in support of hunting. So what he suggested is that hunters going out and looking for animals and then having to come home would have to sort of come up with a new route home. and that this would select for abilities in allocentric perception. The interesting thing is we can see evidence for allocentric perception in hand axes. Occurs very late, certainly by 500,000 years ago, maybe by 800,000 years ago. And the hand axe on this slide is symmetrical in 3 dimensions. That is symmetrical in profile, symmetrical in plan. And if you took this hand axe and put it on a saw and sawed through at any angle, the cross-section would be symmetrical as well. And the cross-section is not available to the stone napper. The stone napper can't see it when he or she is napping the artifact. So it's a perspective that has to be constructed. And so these hand axes with regular cross-sections suggest that the hominins who were making them had basic abilities in allocentric perception. And I did want to show you a really lovely artifact from the Ashmolean Museum in Oxford. It demonstrates a number of the napping things that Nick Toth talked about. But what I wanted to point out is this nice sort of S shape on the edge. This is a twisted ovate. It's really a lovely artifact. And again, it relied on basic spatial understanding of basic spatial relationships, including allocentric perception. And then hominins on late artifacts played around with symmetry a lot. And they started to violate symmetry intentionally, which I think is interesting from an aesthetic perspective. And finally, I don't have time to talk about these very much. Towards the very end of hand axes, the hominins started to make them in the shapes of animals, which I think is very interesting from a semiotic perspective. That is, these are iconic hand axes. And these are probably very late, probably 300,000 to 250,000. This is the time when you find the first possible evidence for iconic objects like the Barricade-Ram figurine. Okay, so what was spatial cognition like 500,000 years ago? First of all, the hominins were imposing 3-dimensional symmetry on artifacts. They were often violating symmetry in aesthetically pleasing ways. They demonstrate technical brilliance. They really were wonderful stone knappers. They had a sensitivity to regular geometric forms. They employed gigantism as an implicit visual effect. And in some cases at the end, they also made hand axes that actually looked like animals. Stone knapping itself may have powered these developments in cognition through embodied and extended resources. So what? I mean, what does that suggest? Well, it suggests that one of the important components of survey knowledge was in place probably before 500,000 years ago. And this is allocentric perception. In other words, this component of modern spatial thinking evolved long ago, before modern humans appeared on the scene. And I think that's a very interesting bit of information about human spatial cognition. And I will pass it on now to Lee, who will talk about more recent times. Lee.
Thank you. See if I can share my screen. Can you guys see my slides? So I'm going to pick up the story with the emergence and development of cultural systems of space in the last 60,000 years. So we're going to jump forward in time a bit. This story needs some context, because over the past 2 millennia, which is not a lot of time in an evolutionary sense, the West has invented many devices for navigating, measuring, representing, and labeling space. There were so many devices, in fact, that traditional wayfinding was actually lost, which is kind of interesting in and of itself. Traditional wayfinding was so utterly forgotten that by the 19th century, when the Victorians encountered it in other societies, they thought that so-called primitive man possessed an animal instinct for home. Fortunately, this is no longer believed, but the same trend continues to this day because, you know, among Western people, knowledge of the stars is pretty rare. and certainly the ability to navigate by means of them is pretty rare. But I'm going to talk about traditional societies, and they deal with space on 3 overlapping scales. From largest to smallest, these are navigating the unknown, traveling the known, and measuring cultural space. As Tom has explained, navigating the unknown involves survey knowledge, where space is organized into a stable map-like framework. This is the allocentric or bird's eye view, in which every point or landmark is related to every other point. In contrast, traveling the known is a matter of route knowledge, and that's the egocentric or personal perspective in which every point or landmark is related to the traveler. And finally, measuring cultural space begins with the body. And that part of the story will connect with the beginning of geometry, which is our formal science of space and shape. Despite the loss of traditional wayfinding knowledge, especially in the West, modern people, even Western ones, use both survey and route knowledge. A personal example comes from living in Colorado Springs, where Pikes Peak always orients us to the west, even in unfamiliar parts of town. In the past 200,000 years, Homo sapiens, that's us, reached and colonized virtually every environment on the planet. For Australia, the Americas, and the Pacific, this migration occurred even more recently, within only the past 60,000 years or less. Navigating, of course, involves keeping track of where you are, relative to where you are going, and of course, relative to where you came from, especially if you have any hope of going back there. So, how did we get from stone tools to such impressive navigation? For millions of years, our ancestors interacted with stone tools in ways that enabled them to appreciate structural features and spatial relations across multiple dimensions. The allocentric view is nothing more than this same ability applied to features and relations of land and sky. The features and relations in question simply differ as to whether they are localized and contiguous, as in objects, or distributed and non-contiguous, as in allocentric wayfinding. Now, there are 2 basic strategies for navigating allocentrically. One is celestial navigation, determining position by means of the stars, planets, sun, and moon. The other is dead reckoning, determining or predicting your position from a starting point, as adjusted by your heading, speed, and drift. Heading and speed are measured, while drift involves estimating the effects of ocean currents and weather. We'll look at celestial navigation in the Pacific, which Tom mentioned at the beginning of his talk. Navigators memorize the rising and setting points of the brightest and most distinctive stars and planets. To aid this memorization, navigators use what's called a star compass. This is a body of knowledge passed through oral tradition, and a mental construct achieved through experience and practice. It's not a physical device, although it has been given just such a form, as you can see in the modern era on the screen. Star compasses locate and name the places where the stars emerge from and return to the ocean. Navigators identify stars as they rise and set, and this lets them know their position and direction. They choose a star on the horizon and steer their waka or canoe towards it. When the star rises too high in the sky or sets beneath the horizon, they choose another star to follow, and so on throughout the night. I've heard that 7 to 12 stars are enough for one night's navigation. In Micronesia, navigators use alignments between horizon stars and ETAC, or reference islands. From the island of origin, the navigator knows that the ETAC lies in the direction of star X. As the journey progresses, the relative direction of the ETAC changes until it falls towards star Y. When the ETAC approaches the direction of star Z, the navigator knows he is near the destination island. Now, what is shown here is downwind sailing. The navigator sets a course for a point upwind of the target island. This is a strategy for improving the chances of finding it. Once this point has been achieved, he turns the waka to let the wind carry it to the destination island. When sailing against the wind, the destination island and ETAC are the same. The navigator tacks left until he considers the ETAC to lie in the direction of star A. He then tacks right until the ETAC lies in the direction of star F. He repeats this with shorter and shorter tacks as the E-tack draws nearer. There's an interesting nuance here, as it is the E-tack that is considered to move and the waka or canoe that is considered to be stationary. This is quite a different conceptualization of the available variables than is found in Western navigation, where of course it is the ship that is considered to move and terrestrial features like islands that are considered to be stationary. Pacific navigators are a great example of combining survey and route knowledge. For example, keeping track of direction in familiar waters involves feeling ocean swells as they refract around or reflect off of known islands. Navigators feel the direction that swells come from, and they note their relation to the guiding stars. And then if the sky becomes overcast, this helps them maintain their orientation. In unfamiliar waters, change in the swell pattern is a good indication that islands or underwater reefs are near. A device used to teach this knowledge is the shell map. Unlike the star compass, this is an actual device. Shells indicate islands or island groups, and sticks show ocean swells and their direction. Since stars aren't visible all the time, the sun and moon are also used. The sun provides a directional point twice each day as it rises in the east and sets in the west. At daybreak, the navigator notes the position of the waka in relation to the rising sun. And as the sun gets higher in the sky, he looks toward where it will set in the evening. At night, if clouds or fog pass in front of the guiding stars, the moon may still be visible, and it is a good indicator of direction, especially when it is located near the horizon. Long journeys into unknown waters meant relying on celestial navigation as the means of fixing position. Clouds or storms could cause sailors to become completely lost, with no way to return home. Whether they were lost or not, the significant differences involved meant that sailors had no way of knowing whether they'd find land. Most likely, they'd go out and look for signs of land until either they found them or they reached the point of no return. And that's when they had only enough supplies left to turn around and try and go home. We're going to look at those signs of land. Visibility at sea is governed by the curvature of the Earth, the height above sea level for both ship and land, and the distance between the two. Large canoes could extend more than 7 meters above the surface of the water. The big island of Hawaii, which is over 4 kilometers high, can be seen from about 150 kilometers away. For an atoll whose highest points are coconut trees, visibility is about 1/10 of that distance, no more than about 15 kilometers. Outside of visual range, certain signs indicate the proximity and direction of land. For example, clouds tend to gather over an island, and of course they can be seen from much further away than the island itself. Seabirds are another indicator of proximity and direction, particularly the white tern, a species that can range up to 200 kilometers from land. Besides birds, clouds, and ocean swells, other useful signs include wind direction, light reflected by lagoons, plants washed into the ocean, sea animal behaviors, localized wave characteristics, bioluminescence, watercolor, and telapa, rare and mysterious flashes of light said to emanate from land like lightning. How about position? In Pacific navigation, sailors keep continual mental track of where they are. So in a sense, they always know, and they don't write anything down. In contrast, in Western seafaring, heading, speed, and time are used to chart the ship's position on paper maps, and that's true even to this day, although it's no longer the only system that are used on board ships. For heading, a compass is used. For speed, in olden days, sailors threw overboard a log attached to a rope with knots tied every 14 meters. As the rope passed through their hands, they counted the number of knots in 28 seconds. Today, the record of a ship's movement is still called the log, and a ship's speed is still measured in knots. It's a little hard to see on the diagram, but the young man in the middle is holding an hourglass, so their time measurement was a bit of an estimation. Western sailors also used local guides. In the first of his 3 Pacific voyages, James Cook took on board the Endeavour an experienced Pacific navigator, a Tahitian named Tupaia, who helped Cook find New Zealand, later died in Indonesia of a shipborne illness. Tupaia drew a map while he served with Cook, today thought to be an attempt to explain Pacific wayfinding to the Westerners. The map does not use Western spatial concepts like proportional distance or geographic coordinates, and many of the islands it depicts cannot be matched to any known. However, scholars are currently using traditional wayfinding methods to try and decipher it. Over land, a traditional method of keeping track of time and distance involves the amount of ground covered in a day's worth of walking. The navigator keeps track of the number of days he has walked, and he knows about how much distance that involves. My favorite account of this comes from Australia. An Aboriginal messenger painted his arm with stripes of mud, one for each day of his journey. On his return trip, he would erase one stripe each day. In the Kalahari, distance and time involved in walking is contextual and understood as such. For example, a woman gathering food covers less distance than a man going out to hunt. Total distance is expressed as the number of sleeps, which is an indicator of how many days, with remaining portions of days indicated by pointing to the expected position of the sun upon arrival. Route knowledge, in comparison, is the ability to construct a sequence of points, landmarks, and perspectives that comprise a path from one place to another. Primates, with one exception, and that would be us, rely on route knowledge, as Tom mentioned in his talk, since they lack the kind of innate positioning or directional system found in bees, birds, and some other species. In our branch of primates, the bipedal apes, route knowledge is suggested by the footprints at Laetoli in Tanzania, where the Australopithecines, one of the earliest bipedal apes, left their footprints some 3.6 million years ago. Members of the group intentionally stepped into the previous footprints, creating a natural trackway. Today, cross-culturally, route knowledge involves establishing, memorizing, and sometimes marking trails and tracks, giving places descriptive and memorable names, codifying route knowledge in stories and songs, and using spatial memory. Route knowledge is a really interesting endeavor, especially in environments that, to our Western eyes, have few distinguishing features. In Australia, Aboriginal people traded goods and information over thousands of kilometers for thousands of years. One of the mines where ochre was collected for trade appears to have been in continuous use for some 20 to 30,000 years. In comparison, the famous Silk Road that once linked the West to the Middle East and Asia began some 2,200 years ago and lasted for only 1,600 years. Some of the longest Aboriginal trading routes were created for paturi, an indigenous plant used for its medicinal and hallucinogenic properties. Paturi was traded over an area of more than 800,000 square kilometers. The Aboriginal trade routes that crisscross the continent are known as dreaming tracks. In Aboriginal cosmology, the dreaming is the period of time when the ancestors took animal forms and created the land's topographic features. The features there today attest to these ancestral journeys. Dreaming tracks aren't just etched on the land, they also live in the memories of the people who inherited the routes from previous generations, who had inherited them as well, creating one of the oldest and longest chains of human memory known in the history of the world. In 2016, 2 Australian researchers recorded Aboriginal stories from 21 coastal locations, including tales of a time when parts of the coastline, now underwater, were dry land. These stories corresponded to geological evidence of post-glacial rise in sea levels, showing that they were transmitted over a period of some 7,000 to 13,000 years. Dreaming tracks and associated song cycles function as mnemonic devices for wayfinding. They provide reliable descriptions and literal directions for travelers to follow, including places they have never personally visited before. The land is the text, and songs and stories are the means of reading it. Associating stories and songs with specific places makes the information easier to remember and recall. This strategy for spatial memory is akin to the so-called method of loci. The method of loci is a technique for associating memorized information with spatial locations, like a street with shops or the rooms of a house. It's also sometimes called the Greek memory palace, a name that reflects its origin as a memory strategy invented and used by ancient Greek orators. When someone wants to memorize a set of items, he mentally visits the spatial locations and associates an item to be memorized with each one. Retrieving the items then involves mentally visiting the spatial locations to see what each one holds. While the method of loci can involve recollected or imagined places, dreaming tracks use the actual landscape. However, both leverage spatial memory, a function of the hippocampus. The hippocampus is a component of the limbic system, the part of the brain involved in behavioral and emotional responses that is sometimes called the old mammalian brain. Besides its critical role in spatial memory, the hippocampus is also involved in consolidating short-term memories into long-term ones. Named after the Greek word for seahorse because of its shape, the hippocampus is famous for becoming larger in the brains of London taxi drivers who are required to pass a test demonstrating that they have memorized the city's 25,000 streets and all the businesses and landmarks on them, and can flexibly plan alternative routes. Storytelling as spatial memory was also once known in the lands that are now weird: Western, educated, industrialized, rich, and democratic. For example, epic poems from the early first millennium, like the Odyssey, were stories in spatial form. Putting stories in the form of a journey, a sequence of spatial events, made those events easier to remember and recall, facilitating oral transmission between individuals and generations. When oral traditions invent writing or come into contact with the idea of it, their stories may take the form of journeys, sequences of spatial events. Here is a page from an Aztec codex that shows the journey from the mythical Aztec homeland to the Valley of Mexico, where they ultimately settled. Most of the content in the codex is pictorial, with little footprints to indicate the idea of spatial connection, while any glyphs are restricted to names, particularly the names of geographic places. Geographic names take a variety of forms in Aztec writing, including historical events, distinctive environmental features, and cultural associations. In the Arctic, Inuit peoples built piles of rocks called inuksut, stones that act as waypoints and mnemonic devices for travelers. These constructions can be remarkably durable. On one such route, the inuksut are thought to be more than 4,500 years old. Using dogs to pull sleds dates back nearly 10,000 years. However, dogs are more than just transportation, since they also have instincts for homing, and these can be less impeded than human senses under conditions of poor visibility. Importantly, dog sled travel is also slow enough that travelers can still feel the natural wind, an important aspect of orientation and direction. Modern means like snowmobiles are so fast they lose the natural wind. The associated loss of orientation and direction, along with the greater speed, increase the chances of becoming lost. Before we move on, let's look at wayfinding in Neanderthals, our cousin species who lived in Europe during the Middle Paleolithic, the period between 300,000 and 50,000 years ago. Remember that modern spatial cognition emerged more than 500,000 years ago. This is sometime after the last common ancestor of Neanderthals and Homo sapiens, who lived nearly 2 million years ago. Now, these timelines are estimates and thus imprecise, and Neanderthals had the same stone tool using heritage, and they had developed impressively complex stone tools. Thus, it's quite possible that Neanderthals had a similar capacity for spatial cognition. We'll examine this possibility through a recent archaeological study. This study analyzed landscape knowledge, navigational abilities, and decision-making at Bau, a French site inhabited by Neanderthals some 200,000 to 100,000 years ago. The study analyzed more than 350 potential sources of raw stone for availability, quality, and distance from the main Neanderthal camp. Comparing availability to exploitation showed that the Neanderthals did not exploit most of the area's resources, including several sites with high-quality stone located very near the main camp. However, for what they did exploit, they could plan efficient routes to obtain the raw materials, and they could identify optimal alternative routes, not only from the main camp, but also from various locations within the area. The ability to estimate access costs accurately implies a location-specific awareness of directions and distances, which the authors of the study claim is best explained as survey knowledge. From this, we're tempted to conclude that Neanderthals and Homo sapiens had the same capacity for spatial cognition. However, territory size and exploration are also influenced by things like sociality and creativity, cognitive domains in which the two human species are known to have differed. Thus, it's not surprising to learn that Neanderthals tended to have smaller ranges than Homo sapiens, and this also admits some possibility of some slight differences in spatial cognition. We come now to the third and final of our three overlapping scales, the cultural measurement of space. Societies measure space in order to do things like construct shelters and estimate the size of fields. Cross-culturally, measurements begin with the body, making man literally the measure of all things, as Plato observed in the early first millennium. An inch was the width of a man's thumb. The palm or hand, 3 to 5 digits across, is still used today to measure the height of a horse, although it has been standardized to 4 inches. A span was about 9 inches, the length of the outstretched hand. The foot, 12 inches, was the length of the average male foot. A mile was 1,000 paces, as counted by the Romans in double steps. Other measurements included the arm span, useful for measuring cloth, and the forearm or cubit, as measured from the elbow to the tip of the middle finger. At some point, measurements transitioned from the body to physical devices like ropes and rods. These not only had more standardized dimensions, they were way more convenient when it came to measuring large things like agricultural fields and monumental constructions. Some of these measurements are quite old, and it's astonishing to realize how old some of these cultural systems are. They were used in Mesopotamia and Egypt more than 6,000 years ago. The measurement standard shown here is made of copper alloy and comes from the ancient Sumerian city of Nippur in what is now Iraq. It defined the cubit as about 52 centimeters, just over 20 inches, which again makes us recollect the forearm. In Egypt, the cubit was defined as 7 palms in length, about 21 inches with a 3-inch palm. As measurements are codified and standardized, they become increasingly involved in calculations. This 5,000-year-old clay tablet from the ancient Sumerian city of Uruk contains the world's oldest documented calculations. One calculation appears on its obverse or front, another on its reverse or back. By the time calculation appears in the archaeological record, it is already impressively complex, suggesting that these cultural systems originated before the Neolithic. As reconstructed, the tablet calculates area for an irregular quadrilateral by multiplying average length by average width. The calculation on the reverse uses different lengths and widths to calculate the exact same area, which suggests the tablet was a schoolhouse exercise. Both calculations involve a standard measurement, the rod, a length about 6 meters long. However, the unequal sides meant the corners were not right angles. With no way of specifying what the angles were or dealing with them in the calculations were necessarily imprecise, as they certainly shouldn't have ended up with the same answer. This suggests that in the 4th millennium, people didn't quite yet know how to handle shape and size and angles as factors in geometric relations and calculations. However, the calculations were likely accurate enough for the purposes they served at the time. Dated to about 1,500 years later, this old Babylonian mathematical tablet contains a square and its diagonals, not just a diagram, but a study of geometric shape and relations. This too was likely a schoolhouse exercise. The number in green approximates the square root of 1/2, while the number in blue is its reciprocal, the square root of 2. The first number is the hypotenuse of a right triangle with sides of equal length, 1/2 in this case, since 30 is half of 60 in the sexagesimal or base 60 number system used in Mesopotamia. Both calculations are accurate to 6 places, when compared to our modern versions in decimal or base 10. Simply, the mathematicians of the Old Babylonian period had figured out the geometric relations of right angles. Here is another Old Babylonian mathematical tablet known as Plimpton 322. While its purpose remains a matter of ongoing debate, it is usually considered to be related to Pythagorean triples, prefiguring Pythagoras and his famous theorem by over 2,000 years. While column 1 is mathematically related, its purpose remains unclear. Here is a quick and admittedly modern calculation of the angle enclosed by the adjacent leg and hypotenuse in columns 2 and 3. I want to highlight the fact that these angles do not appear anywhere on the tablet. Interestingly, the angles increase within a very narrow range, which isn't something we might predict given the complete lack of any pattern in the lengths given in columns 2 and 3. While this still doesn't tell us what the tablet means, it does suggest a methodical and rigorous exploration of the properties of right triangles. At roughly the same time, mathematicians in Egypt were calculating areas and volumes for rectangles, circles, triangles, trapezoids, cylinders, and of course, pyramids, as shown by the Rhind mathematical papyrus. Written in the early 2nd millennium, the Rhind papyrus was likely a copy of an earlier text, although we don't know how much earlier. Of note, the Egyptians, like the Babylonians, were only using right angles in their calculations at this point in time. By the 1st millennium, Babylonian mathematicians were dividing the circle into 360 degrees, something again that reflects their sexagesimal or base 60 number system. What is shown is a tablet from the Assyrian city of Nineveh in what is today Syria. The city is thought to have been the location of the famous Hanging Gardens of Babylon. In this system, which we still use today, a right angle is 90 degrees. The groma, an early survey instrument for estimating right angles, also emerged in the early 1st millennium in Babylon and/or Egypt. It consisted of 2 sticks set at right angles on an arm attached to a main pole. Cords whose ends were weighted descended from each end of both sticks. The groma would later be standardized by Roman surveyors who used it to build about 80,000 kilometers of arrow-straight, stone-paved roads, primarily for their military as it tried to conquer the known world. In the mid-1st millennium, and borrowing much from the Babylonians and Egyptians, Greek mathematicians like Euclid were also investigating and codifying space and shape, creating the science we know today as geometry. Here the story becomes quite familiar, so this seems like a good place to end. But to tie it all together, we started by describing our ancestors' interaction with stone tools over millions of years. This interaction ultimately yielded the ability to appreciate sets of features and relations in objects in multiple dimensions. The ability to appreciate sets of features and relations that were localized and contiguous later expanded to include sets that were distributed and non-contiguous, which is allocentric wayfinding. The geometric diagram can be regarded as the same ability applied again to sets of localized contiguous features and relations, but now in a medium that permitted their manipulation and analysis, subsequent to the development of cultural systems for measuring space, as well as, of course, numbers. These things in turn would ultimately provide a foundation for a later extension to distributed non-contiguous sets, as in geographic coordinate systems. We've covered space and shape across significant spans of time, multiple species of bipedal apes, including us, and the domains of wayfinding, measuring space, and dealing with shape. Thanks very much for your attention.